It's a pleasure to be here. In fact, many years ago, I was one student like yourself, thinking of where I was and what I wanted to do for my future career. And that's the subject of actually navigation, is to figure out where you are and where you're headed. Okay, so that navigation basically answers the question of where are you in space and how are you oriented in space. I'm going to be talking about a brief overview of avionics navigation systems, and then I'll focus a bit on what we have at Concordia, which is first of its kind. It's a Google Earth flight simulator. So we do have a flight simulator at Concordia. It's the only university in Quebec that has a flight simulator. It's courtesy of Mectronics, which is a spin-off from Concordia University that started in 1987 from alumni of Concordia, and they donated a flight simulator for our labs. And so we're very pleased that they did that. So here's the outline. Introduction, a little bit of an introduction to Concordia University. I don't know if you, how much you've heard about Concordia before, and so what sort of degrees we have there. And then I'm going to cover an overview of navigation and the main techniques of navigation. I'll focus on terrestrial radio navigation, satellite radio navigation, and also inertial navigation systems. I'm sure everybody heard about GPS. So GPS is a means of navigation using satellite radio signals. Then I'll briefly mention flight control as well, and I'll end up with showing you the flight simulator that we have at Concordia. So this is the new building of engineering and computer science, Concordia University. It's the EV building. It's a very interesting concept. As you see, it's beautiful architecture. And it's an interesting concept because it houses both engineering and visual arts. That's why it's called EV, E from engineering, V from visual arts. So both artists and engineers are in that building. We have several undergraduate programs in engineering, building and civil engineering, and environmental, electrical and computer engineering, mechanical and industrial engineering, and we have computer science as well. There's also several graduate programs, all that you see listed here. I am particularly associated with aerospace engineering. I teach several courses for both undergraduates in mechanical and electrical engineering, because we do not have a Department of Aerospace at Concordia, but also courses in aerospace engineering for graduate students. The teaching vision in aerospace at Concordia is as follows. The idea is that you have some building blocks that you're basically studying here, and you're going to study more if you want to join Concordia. The three basic pillars of aerospace is fluids, structures, and dynamics and control. So you have some basic courses on fluid dynamics, some basic courses on structures, and some basic courses on electrical systems and control systems and dynamics. And so these are the building blocks for you to be able to have two main streams. So usually departments in aerospace are, or used to be called, aeronautics and astronautics. And so aeronautics basically covers aircraft and everything that happens on the atmosphere, and space systems cover spacecraft that will go and be deployed outside of the Earth and will orbit. So we have, the idea is to have both of these systems, with certification being a course that is very important, because if you are an engineer, you can have beautiful ideas and design beautiful systems, but if they're not certified, if they're not guaranteed that they're safety critical systems, if they're not guaranteed that they're safe and not certified by an authority, they cannot fly. Okay? So any little thing that you do, any little change that you do to an existing aircraft needs to be certified. Same thing for a spacecraft. So certification is a very important course that feeds both of these streams. And of course that the focus is to be very strong on the basic fundamentals of mathematics and physics. But also it's important that then you apply these fundamentals to design and build actual engineering systems. Okay? So we have teams designing and building small aircraft for the Capstone project, and we have teams designing and building small spacecraft. I don't know if you heard the news. Last year, it was the first time ever that in Canada there was a competition to design a small satellite, what is called a CubeSat. So a satellite with cube dimensions. Dimensions of around 1 meter per side, so 1 meter cubic of volume. And Concordia has won the first competition that was last year. Okay? So now we have a very strong space systems since last year. Of course, that to design and build these things before you actually go and spend several hours testing equipment, equipment is expensive, hours of engineers is expensive. So it's always a good idea nowadays with the advent of computers and how cheap computer power is, how inexpensive it is, to use systems integration and simulation first. And that's where the flight simulator becomes very important. So a little bit about civil airline navigation systems, just to give you a historical perspective. I really enjoy history, and I think it's very important for us to know what happened in the past so that we learn from the mistakes of the past to make sure we don't do them again. And also it helps us look at the future with a different view. So the first powered flight, as you know, probably was in 17th of December 1903 by the Wright brothers. They owned a bicycle shop in Dayton, Ohio. And in fact, they flew in Kitty Hawk, North Carolina. And you see here a flight, the first flight of the Wright brothers aircraft. This was in 1903. And it was not the first flight, but it was the first controlled flight, which is one of the topics of this talk today. And that's why it's very important, is that it was the first flight where the pilot could have active control of the flight. And you see here the pilot actually basically leaning on top of the aircraft. And it could control with the hands, it could warp a little bit the wings. And it would also have an elevator up front that would go up and down and would control the pitch of the aircraft. Okay, so it was the first controlled flight, and they were successful with that. First controlled and powered flight. And it was more than 100 years ago. Then, you probably have not heard about this, but the first airline, the first commercial airline actually appeared very, very early in 1914, just before the First World War, actually. It's a two-seater, it's an airboat, as you see here. It was called St. Petersburg Tampa. And it was already making commercial flights by 1914. Then the First World War came and stopped a bit the commercial airline business, and it really took off with the de Havilland Comet 1 at around 1952, so after World War II. And so that was the first successful commercial application of an aircraft. Then the Boeing 707 in 1957 was quite successful as well. You see here that the pictures now become colored instead of black and white, but still did not use fly-by-wire technology. So the way that the first aircraft would work is that the pilot has a stick and would move the stick or the yoke, and as the stick is moved, there's all a set of pulleys and connections to a surface at the back, which would be the ailerons or the elevators, and then the ailerons would move, and this causes forces and moments in an aircraft that makes it accelerate and turn. However, of course, with mechanical systems, we have the tear and wear. And also, mechanical systems require a lot of maintenance that sometimes is expensive. So when basically electrical systems became quite successful, one obvious idea would be to, okay, so the pilot still has a stick, but instead of communicating mechanically to the surface, why don't we just create a voltage? And that voltage is communicated by a wire to an electric hydraulic system that would then have enough power to move or deflect the surface. So that's called fly-by-wire, because it's what it is. It's basically a wire that communicates the signal back to the surfaces. The Boeing 707 still didn't have this technology, but one very early, and the first, in fact, application of this technology was in 1969, the Concorde. Here's an example of a beautiful design, engineering design, that ended up not being that successful, and now it does not fly anymore after 2003 because it was very expensive. So in engineering, when we're designing, we also have to take into account the budget and take into account how commercially viable it will be. The Concorde was a beautiful airplane, was an airplane that had lots of new technology, that pushed a lot of research, and unfortunately had to be discontinued because it was not commercially viable. It was the first aircraft that had fly-by-wire technology, although it was analog technology still in 1969. But then we had the spread of transistors and digital systems. So the Airbus 300 still did not have also fly-by-wire technology, neither the Boeing 767, but the 777 was the first Boeing to have fly-by-wire, but now digital, not analog. So basically digital technology, I don't know if you are aware, but digital signal basically is formed by small units of information called bits that can be either 1 or 0. Basically on and off. You could, if you want to classify a temperature, would be hot or cold, but doesn't have intermediate possibilities. But of course that if you join 2 bits, then now you have 4 possible combinations, 0, 0, 0, 1, 1, 0, or 1, 1. So now you have 4 possibilities. And if you join more bits, if you join 8 bits, then you have a byte. And so digital technology communicates based on bits. So signals that are discretized, signals that are basically quantized, rather than analog technology where the signal can basically have any possible value. And so this Boeing has digital technology. More recently, there was a big, as you see here, a big spread up with new technology between, this was in 1995, really between 1995 and 2005, not much was going on in terms of different aircraft designs. Basically, people would get a very successful design and would just try to basically make it longer so that it would take more passengers. So it was modifications, little deltas in modifying existing aircraft design. But the Dreamliner, Boeing 787 and the Airbus 380 really have complete new technology. And that has been the last really dramatic increase in sophistication in navigation systems has been with these 2 aircraft. The Airbus is already flying, as you probably know. The Dreamliner Boeing 787 has had some problems with batteries, and I don't know if you're aware of the news that they were actually discontinued the flights of the Boeing 787 until they figure out what the problem exactly was. There were no lives involved, and there's no problem, but there were a few issues that prompted them discontinuing the Boeing 787 to fly. Okay, so this was a brief outline of how things evolved in navigation systems. Ever since we had the Wright brothers flight, then obviously for us to be able to go from airport A or point A to point B, we would need to know at each time where we are and how can we basically guide the aircraft to go in a given direction. If we know where we are, we still want to know, okay, so now we're here, we want to go there, so what is the path that we should follow and how to do that? So that's what is basically the science of navigation, and I would like to transmit, hopefully, my passion for navigation to you today. Okay, so let's take a look at how flight evolves and what are the most important phases of flight before we actually focus on the techniques of navigation. So terminal area consists of a departure and approach phases. Takeoff begins when the aircraft is taxiing onto the runway, and it goes all the way until you rotate the nose of the aircraft. And so the gears are up. En route leads from a given, is when you're going from a given origin to a destination airport. Approach begins when you are acquiring the first landing ad. So basically when you get the first navigation signal that is going to add you to land is when the approach begins. Sometimes there are missed approaches. One of the problems right now is that there's lots of traffic congestion in airports, especially big airports, like for example in Chicago O'Hare Airport or JFK in New York City. These are airports that have a lot of congestion, and so therefore in many cases there are human errors, or there are possibly more than one aircraft that are going to be trying to land, and there's the need unfortunately to be very alert to these cases and have a missed approach. It happens more often than what you probably think, but also can be initiated at the pilot's option instead of traffic controller's request. And it could be because of poor visibility, poor alignment, equipment failure, or as I said, conflicting traffic. Then of course there's the phase of landing, which basically consists of landing the aircraft on the runway. Surface is aircraft movement from the runway to the gates or hangars, in case the aircraft is going to go to the hangar. And then there's one phase called weather, which is used when the visibility is restricted. There's two ways to fly aircraft, two rules. One is called visual flight rule, the other one is called instrument flight rule. So visual flight rule is basically looking out of the window. If the weather is good and requires less training from the pilot than the instrument flight rule, if the weather is reasonably good, you can look out the window, you can see, for example, you're flying over Paris, you see the Eiffel Tower, you know where you are, right? When the conditions are not good, then you have to fly solely based on instruments, an instrument panel that you have in the cockpit. That's called IFR, instrument flight rule. The takeoff. For takeoff, you need to know the highest ground speed at which aborted takeoff is possible. Because beyond a certain speed, you really have to take off. You really have to rotate, and if you want to then come back to the airport, you need to take off, go around, and then come back. You can't abort it anymore because that could cause an accident. You're going at a too high speed to be able to do something about it. And so when the nose is lifted up, it's called rotation of the aircraft. The approach needs to know what is called the decision height, which is the altitude above the runway at which approach must be aborted if the runway is not in sight. Okay? So there's a given altitude that if you don't see the runway, it could be bad weather, but at some point you need to see the runway. And that point is the decision height. If at that height you don't see the runway, you have to abort your landing. And landing begins at the decision height when the runway is in sight and ends when the aircraft exits the runway, okay? And goes to the gate. So these are the phases of flight. Now, okay, so that's the way you fly. So those are the different phases, but to fly, you need a vehicle to take you. And so we'll talk a little bit about aircraft vehicles now. An aircraft can be civil or military. That chart I've shown you was just about civil aircraft with all of the technology throughout the years. Civil aviation industry consists of the air carriers, as I showed, the airliners, but not only. Also general aviation, which are small aircraft, or corporate jets, like for example Bombardier corporate jets. And operating either in developed areas with ground stations. So for example in North America we have ground stations. We'll talk about what these are. VOR, DME and LORAN are basically radio navigation, terrestrial radio navigation systems. Or over the oceans, and over the oceans you need a global navigation method, a long range navigation method. And usually use GPS, inertial navigation, or Omega navigation ends. Military aircraft, this is the only thing I'm going to talk about military aircraft, is that they can be divided into several categories, and you have the categories listed here: interceptors and combat air patrols, close air support, which deliver weapons, interdiction, that strike behind enemy lines, cargo carriers that drop cargoes, reconnaissance vehicles, typically nowadays UAV. UAV stands for uninhabited air vehicle. So you probably heard a lot about the Predator and how much the Department of Defense of the United States is using these vehicles for reconnaissance to find terrorists in Pakistan and Afghanistan and all of those areas. So UAVs now are pretty much used, unfortunately, only in military applications. I do believe they could have very good civilian applications, and I think there's an industry out there waiting to start with these applications because it could be actually a very successful industry, right? So search and rescue, forest fires, going inside buildings and detecting gas leaks or any chemical that can have a leak instead of a person being involved. So being to environments that are hostile to humankind. And there's also the ones that can take off and land vertically, okay? So the short takeoff and landing. There's also, which are called the STOL, STOL aircraft. There's also the VTOL aircraft. VTOL stands for vertical takeoff and landing. So you could have helicopters that can take off and land vertically, but there's also aircraft that they can rotate their propellers up 90 degrees and then take off vertically and land. Okay, so now let's go then into the navigation. So this was basically just a basic overview of what you have in civilian applications, in military applications, and how navigation systems evolve. So let's see really what is navigation now. As I said, basically is the science that determines where you are and how you are oriented in space. There's a very interesting movie called Castaway. I don't know if you have had the opportunity to see. Where somebody has an accident in a UPS, I believe it's an UPS aircraft to deliver a package, and ends up in an island, and then wakes up, doesn't know where he is, right? And so it's quite interesting to try to follow the script to see, how he's going to figure out where he is, how he's going to basically find food, all of those things. So basically, it's easy for you sometimes to navigate because we have so many things that we use to navigate. But if you imagine yourself in the middle of the ocean, in the middle of nowhere, where looking around in any direction, it looks the same, you will appreciate that it is very important to have navigation means. Of course, GPS nowadays is the best well-known, and it's an all-weather system that works with good weather, bad weather, and it's pretty much used all around. But there are other means of navigation. So translational state vector is the vector of the 3 positions and 3 velocities that fully describes the translational motion of the vehicle. So when the vehicle translates, of course, in 3D space, we have 3 positions, and we have the derivative of these 3 positions, which are going to be the 3 velocities, x, y, z. This is called the state vector. The navigation sensors can be located either in the vehicle or outside, typically on ground, which is called surveillance. For example, we can have a GPS inside the vehicle, and we can have a radar in the control tower for air traffic control. Okay? So these would be 2 different ways to place the sensors. There are sensors on the aircraft, sensors on the ground stations and airports. Automatic dependent surveillance is a term that for the reporting of the position measured by the sensors in an aircraft. So as the sensors measure the position, they report the position, and you see this in the cockpit in the instrument panel, also now on a computer, on a cockpit computer. And guidance is the handling policy for the vehicle to make it follow a trajectory coming from the trajectory plan. So there's a computer, there's a management system inside an aircraft, which is called the Flight Management System, FMS. And so basically the pilots, when you get to the airplane, usually the pilots are in the cockpit already, and what they're doing is that they're basically putting in all the data in the computer on board, in the flight management system of all of the flight plan that they want. And so the flight management system, what it does, it receives this input before you start the flight. And as you go on the flight, it will receive weather reports and the signals from all of the navigation sensors, and it keeps recomputing your flight path to be followed. So there's a given trajectory plan. You want to go from point A to point B. Possibly you want to pass through point C and D in the middle. And the flight management system knows this, but then you have to make sure that given where the aircraft is, and given that it should be following that path, that you guide it to go from where it is to where it should be. And that's guidance. That's called guidance. So guidance determines the approach to be followed to go from here to there. For example, if I want to follow that wall and I'm now here, I have several possibilities. I could just go straight to the closest point on the wall to me right now, just walking in this direction. Then when I reach the wall, then I walk in this direction. That's one possible guidance method. But if I actually need to follow a target, and if the target is right now there, it's not so clever to go towards the target because the target has a velocity, and by the time I reach there, the target is gone. So it might be better to actually walk in this direction so that I can meet the target. So all of these are different guidance techniques. So guidance has 2 meanings that are different from navigation. They're not the same. And in fact, these systems are called guidance quite often. Guidance, navigation, and control. Okay? G and C. Guidance, navigation, control. There's conferences about this subject. So the meanings of a guidance is to steer towards a destination or trajectory of known coordinates from where you are, from where the aircraft is right now, and to steering toward a destination without explicitly measuring the state vector. So when we steer to a destination, you're not necessarily computing all of your coordinates of position and velocity. You might, for example, just be computing, let me give you the example of the wall again. Instead of knowing my x, y, z position, I can just know my distance to the wall and my bearing to a given point of the wall, let's say to that point there. So I know the angle at which the line connecting me to the wall is, at that, relative to that corner, so relative to the wall, and I also know my distance. And so by just working with bearings, angles, and distances, you can also navigate. You don't need to actually know your precise x, y, z position necessarily. There are 4 categories of navigation. Radio systems consisting of network of transmitters and receivers, like for example GPS, where the transmitters are in a satellite, or VOR and DME, where the transmitters are in a ground station. There are celestial systems, which are not so much used anymore, but the sailors in the 15th century and before used a lot to navigate from the stars. They have what is called an astrolabe that would measure the elevation of a star, and by measuring the elevation of several stars, they could then do triangulation and solve some trigonometry to figure out where they were. So by looking at the sun and the stars, like the North Star and the sun and other stars, they could figure out by trigonometry where they were. So that's called celestial systems. There's mapping navigation systems. For example, Mars rover. So Mars rover, there's no GPS in Mars, as you know, right? So there's no ground stations there. So basically, one way you can navigate is just look at photos, and because there have been other missions to Mars, one has photos from certain parts of Mars. And so if you come back to the same place, you have photos, you can have landmarks, and you can navigate by being based on the landmarks. For example, in this classroom, there's a board there that is green, so that's a landmark. So I could know by just looking at and having a camera that collects a picture of the wall there, I could know how I am located relative to that landmark, and then navigate by, following some landmarks. So that's called mapping navigation systems. They compare an image with a map that is inside a computer. And finally, you have inertial and dead reckoning navigation systems, and these are based on Newton's laws. So they basically use gyroscopes and accelerometers to measure acceleration and angular rates. And by integration of acceleration 2 times, you get position, right? So integrate 1 time, you get velocity. Integrate the velocity, you get the position. That's inertial. Dead reckoning, you start with the velocity. Yes?
Sorry to interrupt.
No problem.
Could you comment on the relative accuracy of those 4 systems? Because it seems to me that number 3, the mapping, would have some inaccuracies.
Right. So this all depends, of course, that it all depends on what kind of sensor you have. So the mapping would depend on the accuracy of the camera. So I agree that in general, this would be more inaccurate, but it all depends on how good the technology you have. With CCD cameras, then things improved a lot depending on how many megapixels you have and all that. Celestial systems are by far the less accurate, especially because now there's no really new technology that I'm at least aware of that is being developed to improve on this old technology. Radio systems depend. For example, VOR, which you'll see in a while, will give you a couple of degrees of accuracy in general of a bearing, of an angle. And GPS is quite accurate. If you do differential GPS, you can get down to a centimeter level accuracy. And inertial has a problem. Can be accurate, but usually what happens is that the error increases with time because you're integrating. And gyroscopes have things such as biases. So there's a little drift in a gyroscope, which is a constant. So we all know now, you had calculus, right? When you integrate a constant in time, then the result is that constant times the time that is elapsed. So as the time increases, the error increases. Okay? So that's what the problem is of inertial. So inertial is not really used by itself as standalone. It's usually used with GPS, together with GPS, integrated with GPS. So what you do is you use the inertial, you integrate the equations, and as the GPS, so this is the one that supplies information at a faster rate is the inertial navigation system. The GPS comes at a slower rate, and each time a GPS measurement comes, you basically reset the error of the integrator, and then you start again. That's how they go to increase accuracy. Okay, so the techniques of navigation, it's similar to the other slide, but not quite. So there's one technique that's called triangulation, and that's the basis of everything. So I'm sure you're covering trigonometry in your classes, or you have covered at some point. Trigonometry is the key. Triangles is the key navigation. You basically get a measurement. I'm here, I get a measurement to that corner, I get a measurement to the other corner, I know the distance to that corner, the distance to that corner, and I know the distance between these 2 stations that would be at the corner, so I have a triangle, and now I resolve. Okay? So based on angles and distances, I can resolve using trigonometry. That reckoning, we talked about it, found out the position by integrating velocity. Inertial, integrate acceleration. Mapping, you extract features. This we already mentioned. And celestial is by computing your position, measuring elevation and azimuth. So elevation is the angle from the horizon to the star. That's elevation. Azimuth is the angle from north to the projection of the star on the horizon. So that's the angle of azimuth. So you have these 2 angles. If I know this angle to the projection, and then from the projection up to the star, then I basically can locate the star. All right, so let's talk about radio navigation first, terrestrial, okay? And then we'll move to GPS. So there's 3 kinds of waves that you can transmit radio signals. So radio signals are electromagnetic signals. And electromagnetic signals, I'm sure everybody saw an antenna. In fact, most probably, most of you, if not all of you, have a cell phone right now. So a cell phone has an antenna inside, transmits information. You can talk to your friends, right, and receive calls. Okay? So an antenna is basically a wire. and radiates. And this information is an electromagnetic signal, a wave that propagates. You can see that wave. It's not a mechanical wave like the wave, for example, in an ocean that you could see. But it propagates, and you can then receive the information that you transmitted with one antenna, you can receive with another antenna. What happens is that this signal then will induce a voltage in the receiving antenna. You capture that signal, and you have the information. You decode the information. There's three ways, though, that you can transmit the information along the Earth, around Earth. And these three methods are ground wave, a sky wave, and a line of sight wave. So LOS means line of sight, GND ground, and sky means sky. It's obvious, right? So there's lots of acronyms in navigation, okay? You have to get used to it. Okay, so line of sight is very simple. So line of sight means that there's a straight path from one antenna to the other. Let's say this is Earth. There's one antenna here, and there's another antenna there. So these two antennas are in line of sight because there's a straight path directly from one antenna to the other that is not intercepted by the surface of the Earth. Okay? So this would be line of sight. Another way to do it is this antenna could transmit a wave that will be basically bound to the Earth's surface as if it was a waveguide, and is going to be transmitted all around the Earth's surface. That's called a ground wave. Okay? Of course, it's going to have interferences when you go from a solid surface to a liquid surface, like in a lake, right? So it's going to have some problems. Another possibility is that there's an atmosphere, as you know, and there's one layer that is called the ionosphere, where all the atoms are ionized. And that is a reflective layer. So we can also transmit a wave up, and it reflects back down from that. So this would be the ground wave, as I said, and this would be the sky wave. Okay? So these are the three possibilities, three possible waves. Of course, one problem is that they might interfere. You might have two waves coming in at the same time, and they interfere with each other, and you have a problem. And that's what happens here with the ground and the sky wave. So what this is a table of is basically there's different bands, names. A band is basically an interval of frequencies. It's called a band. And they have different names. They go from extremely, super, ultra, very, low, medium, high, and then again very, ultra, super, extremely. Okay? The first extremely, super, ultra, and very are low, and the last are high. And in the middle, you have the low frequency, the medium, and the high frequency. So all of these have also an acronym. We love acronyms in navigation, right? So ELF stands for extremely low frequency, and so forth. This is the frequency interval, okay? And these are the types, the kind of type of waves that can carry these frequencies. So you see that ground and sky interfere up to the medium frequency, and then for the high frequency, only a sky wave will propagate, and starting in the very high frequency, only line of sight will propagate, okay? So you'll see that most navigation systems are here, from the very high to ultra high, super high, and extremely high, including GPS and VOR. They work here because it reduces the interference. Okay, so one of the first is the non-directional beacon. A non-directional beacon, as the name indicates, is a beacon and is non-directional. So we'll basically radiate in all directions. Okay, and it works in the low frequency range and medium frequency range. Okay, in these two bands. And the way it works is the aircraft picks up a signal with the receiver and then will change the heading to home in to the receiver, right? Like for example, a pigeon would do, like a bird would do. Okay? So this sort of mimics the way that birds could navigate. By the way, one of the first means of navigation from sailors was, including the Vikings, it's believed, was to transport birds with them. And then they would release the bird, and if land was closed, the bird would follow a path, and they would just follow the bird. If the bird starts going around, it's because there's no land. Okay? So basically, when we did not have technology that was good enough to navigate, we used nature. Nature has lots of incredibly interesting ways to navigate. Birds, bats, using ultrasound, for example. Okay, an automatic direction finder is the first way to that was invented to detect your direction to the beacon automatically. So there's a beacon that emits a signal, and these waves, if the antenna is very far, you can assume that the wavefront is a plane. It's really spherical, but you can assume it's a plane. So wavefront is, for example, if you see a wave crest always coming in, it's the part of the wave that has the same phase. Okay, so you get all of those points together, those form a front. That's called the wavefront, and they propagate, right? So for all of the crests propagate, there's also the nodes, they propagate as well, right? So that's a wavefront. And if they are planar, what happens is the following. If you have a loop like this of wire, right? And if the loop is not perpendicular to the wave signal, let's say that the signal is coming actually from here, and it's not perpendicular. So the wavefront is coming from here. So we'll get to this side first, and we'll induce a voltage there. And then we'll keep propagating and get to the other one later. And so, which means that there's a voltage difference between these 2 points, and there's a current in the loop. So if you detect the current in the loop, it's because you're not perpendicular to the direction of propagation. If you're exactly perpendicular or orthogonal to the direction of propagation, then the voltage is basically induced at the same time in both end wires, and there's no current. So basically what people would do in the good old times, there would be a third person in the crew instead of the pilot only and the co-pilot. There was also a navigator, okay, called a navigator. And so they would actually turn this manually until they see a zero current, a null of the current. Now it's not done like that. You can actually rotate things electrically speaking, right? So you can have a signal by a rotating antenna that rotates in all directions, or you can have basically a bank of different antennas distributed in a circumference around you. You can switch one on and then the other one on and then the other one on. And so the pattern is rotating without actually physically, mechanically rotating, right? So now it's done electrically. So of course then when you have a null current, you know where the direction is of the signal. This is used still today in aircraft to detect, for example, the direction to the airport. If you're out there, you can't see the airport, you put in the frequency at which the airport is transmitting the information, and it will give a needle that will indicate the direction, so then you just turn the aircraft in that direction. But the drawbacks is that there's distortion of the electromagnetic waves in the low end frequency and medium frequency, although this can be corrected by calibration, but calibration is expensive. The desired path of the ADF signals is by ground wave, which are prone to sky wave interference as well, as I said. In these frequencies, you have both ground and sky. So there's interference. And changes in the conductivity of the Earth at solid water interfaces will deflect the propagating signal from a straight line and induce errors. Okay? So basically, when you have different interfaces, an interface between different conductivities, such as Earth and solid. So people created then later what is called the VOR. And VOR stands for VHF, the V from VHF, very high frequency, omni-range. So basically what it allows you to do, the VOR, is that you now have from a given station, let's say you have a coordinate system, from a given station, you're capable of having what are called the radials. In any direction, in any angle, you have radials coming from the station. You can detect an aircraft. You can give the bearings of the aircraft in all of these radials. It's a continuum of possibilities of radials. It's difficult to combine compass headings with ADF. Before, instead of having the VOR, you had your compass, so it would tell you magnetic north, and you have the ADF, which will tell you the direction to the station. And you have to combine these two. Okay? So all has been done now with the VOR. It's way easier. There was a predecessor of this, which is called the AN range, which actually started in Second World War, still with Morse code. So for example, you would have 2 beacons. One would be a dot, one would be a dash, right? And this would even be used to landing. So if you're landing and you hear dash, dot, dash, dot, dash, dot, so basically you know that the runway is in sight. If you hear too many dashes, then you probably need to turn left. Too many dots, you need to turn right, right? So that's how it worked. And this system is at high frequency. So here's how it works. It's actually a very interesting idea. There's a building in Montreal that has, I'm sure you already noticed that has a beam that rotates around at night, right? So imagine that is one of the signals. It's a rotating signal. There's a beam that is rotating. And imagine that in the buildings around that building, Hydro-Quebec would switch on the lights at the same time in all the rooms in all those buildings. Okay? And they would be synchronized, but the lights would only switch once per turn of the rotating signal. And they would be synchronized such that you would receive both signals if you're in north. And so by just measuring the delay of the signal, you can know in which direction you are. Because if you're at north, you have no delay, right? If you are in east, then it's a quadrature delay, right? And if you are 180 degrees, it's a phase shift, right? Completely phase shift of 180 degrees, and so forth. So by just measuring your delay, you can know where you are, and that's how VOR works. So there's two signals. There's a rotating signal and an omnidirectional signal. Now, these are not light signals. These are radio signals. But there's one that propagates to all directions, and there's another one that is directional, that is rotating all the time. And that's how it works. So basically, by determining the phase of these two signals, you get your measurement of your bearing to the station. So bearings to the station, let's say the aircraft is here, are these angles, and they're always positive clockwise from north. So if the angle is, for example, if you're here, the angle would be 270 degrees if you're right there, okay? Because it's positive from north and clockwise. So that gives you angle. So now with this system, if I had a VOR station there on the wall, I could already know what is my angle to the station relative to north, right? But I still don't know the distance to the wall, which is another thing that is important. To measure distance, there's an equipment called distance measuring equipment, and here's another acronym, DME. And the way it works is as follows. Instead of being the station, as in the VOR, transmitting the signal, it is the aircraft that interrogates the station. So of course, there's a maximum capacity problem here. You can only have so many aircraft interrogating at the same time, but there are several stations, and you can always change the frequency and interrogate another station, or wait and interrogate later if the capacity has been reached, maximum capacity. So the way it works is the aircraft sends a signal to the station waits for approximately 50 microseconds, and then retransmits an answer back to the aircraft at a different frequency related to the first. And the aircraft receives that, and assuming that the signals will travel at the velocity of light, then obviously 2 times the distance has to be c times the time that it took to in transit. So of course, from the difference in time that you measure from when you transmitted to when you received, you need to discount the delay that the station had, where nothing happened, everything was idle, right? So you subtract 50 microseconds from the time that it took the signal to go to the station and come back, and multiply by c, divide by 2, you get the distance. That's how this works. And then here's a little slide now on math, which is very important in engineering. Don't make no mistake about it, right? Mathematics is essential. So once you have all of this technology, now you have to use them and integrate them. How do you do it? Trigonometry is the key, right? As I said, triangulation. So let's say you have a station on point A, you have a station in point C. You know obviously what are the coordinates of the station, so you know the distance between the stations. So you know this leg here, C to A, this length, and your aircraft is at B. So now it depends on what system you have. You can measure 2 angles, you can measure 1 angle and 1 distance, you can measure 2 distances, and then you just have to triangulate and use all of your favorite results, Pythagorean theorem, if it's a triangle with right sides, or the law of sines and the law of cosines, if it's an oblique triangle. Okay? And so you can figure out where you are just by that information. So here's a little example so that instead of just me talking about it, you think a little bit about it. Here's a typical example of how we could use navigation, local navigation. An aircraft receives measurements from 2 ground stations at the same time. Station 1 is located at 0, 0, and the VOR measurement indicates the aircraft is in 60 degrees, right? So you draw a picture, like always in engineering, the first thing you do, right? So you have VOR station 1 is at 0, 0, which is there at the origin. That's station 1, right? And then it indicates that the aircraft is in the 60-degree radial. So 60 degree counting from, this is north, 60 degree there, so that means 30 degrees there. Okay. And then you get a second station that is located at 100, 0, right? So 100, 0 would be here, let's say. And that station has a collocated VOR DME. Collocated means that the same station has both a VOR and a DME. So you can get both the bearing and the distance from the same station. So puts the aircraft in 330 degrees radial. So here you go. You count from north. 330. So 270 is like this, right? So to 330 you have 60 more to go. So this is 60. And if this is 30 and this is 60, this is 90. So there you go. So you have a triangle with right angles. So now it's easy to determine what is the distance. And also this distance is 50 kilometers. You know this distance is 100, so you just trigonometry can easily get. Using Pythagorean theorem, you can easily get your distance to station 1. And then the coordinates, you just use sines and cosines, right? So this shows you how important trigonometry is in navigation. It's essential. GPS. So GPS is what you all have probably in your cell phone, right? In your iPad. So GPS, they are everywhere. You take a taxi, they have a GPS, right? So they're everywhere nowadays. How does it work? So the frequencies of GPS is 1,575 megahertz. That's one frequency, L1. And there's a second frequency, L2, which is 1,227.6 megahertz. So it's line of sight, okay? So we're using line of sight. It's modulated by what is called code division multiple access. So each satellite has its own code, and all have multiple access to the spectrum. And so you divide the information by having a different code. So you receive all of the satellite messages at the same time. You have a copy inside the receiver of the code of each satellite, what is called the pseudo-random code. And then basically what you do is a correlation. You compare the signal that you received with the copies that you have from all satellites, and you determine which one it is. That's what CDMA means. It's, there's a coarse acquisition signal, which is a less precise signal. And there's also a P signal, which is called a precise signal, that is way longer than the CA code, and is also encrypted for military purposes in the Y code. So the P and the Y and the coarse acquisition code all come in the L1, which all receivers will have access to. And then there's the L2 will be modulated just by the precise code. Okay? So most receivers will just use the coarse acquisition code. And by the time that, some time ago, there was one thing called selective availability in GPS that probably you haven't heard of. Selective availability was a signal that was an intentional jitter in the signal, so that civilians would not be able to use that signal against the United States in any military application, any enemy or something like that. But that was switched off. So when you had that, the precision of vertical determination of your position could be as bad as 100 meters. Okay? Now is in the around 10 meters if you have a standalone GPS. But if you have the differential, which is 2 GPS stations, it can go down to centimeter level accuracy. It works with 3 codes, 3 segments, sorry. There's the user segment, which are all the receivers, such aircrafts, boats, you, in your cell phone, for example. There's a space segment, which is a constellation of 24 fully operational satellites. It's more like 29, but at any time 24 are fully functional. The orbital planes, there are 6 of them, and there are 55 degrees of inclination. So if this is Earth, that means that there would be 55 degrees of inclination. So the plane is more like that, right? Where the satellites do their orbit. And you have about 4 satellites per plane. 6 times 4 is 24, right? And each satellite orbits Earth every 12 hours. So if you stay in the same position and you listen to the satellite, you'll get the signal of the same satellite about twice a day. Reliable operation of 24 satellites started only in 1994. Okay? The control segment is what controls all of the signals and monitors. So there's monitoring ground stations plus a master station. So the ground stations receive the signal of the GPS, transmit to the master station, and the master station looks at any errors that are in the signals, correct them, and re-upload to the satellite. So this is continuously being monitored. Here's some pictures that I took from Wikipedia. There's some nice application where you can see how many satellites are visible, okay, at each given point. This gives you a map of the stations. So these are the control stations distributed around the globe, and that's the control segment. And the user segment would be, for example, an aircraft. Okay. The GPS equation, I don't want to enter into too much detail, but the idea is that GPS works with time of arrival. And that's what the problem is. You need to have precise clocks. If you're trying to compute a time difference of arrival, let's say the difference between signal of station 1 and signal of station 2, Loran is such a case, you don't need such good clocks. They just need to be repeatable. They can give you always the same error. It could be a large error. It's always the same. When you subtract, you cancel the errors, right? But if it's time of arrival, you need a very good clock. The receivers have inexpensive clocks, of course, but the clocks that go on the satellites are atomic cesium-rubidium clocks. They're very, very precise. Okay? You need that. So the transit time, which is the time between the received signal from satellite K minus the transmitted signal from satellite K, will have a delay from the ionosphere, because the propagation in the ionosphere has a delay from the troposphere, which is another layer closer to the Earth of the atmosphere. And if it wasn't for these delays, it would just be the distance over the velocity, and the velocity is the velocity of light. The distance, you don't exactly know what is the distance of the user to the satellite, so you have to estimate. You have a model of the satellite position, and you integrate that model in the computer. But there's always an error, which is called the ephemeris error. Okay? So that's what the equation of the satellite is. Then what happens is, though, that this would be the ideal world, but the received time, the time you receive, is not the exact time. It's the time plus error, one of them being the bias of the clock. The transmitted time of the satellite is not the precise time. It's the time plus error, small error, because they're good clocks, but nonetheless, there's a bias. So there's a bias in the clock of the satellite. There's a bias in the receiver clock. There's multipath error, which is error due to the fact that you have several possible paths for the signal. The signal can come directly to the antenna or can reflect on a pond and reach the antenna. So there's several signals that interfere. So the measure arrival time is the true received time plus a bias plus the multipass plus random error. There's always a random error in electronics, right? Because electronics heat up, and because of the temperature and the agitation of the electrons, there's random error. The transmission time of the satellite is the real time plus also a bias. So when you replace this and that here, so the received time and the transmitted, you get this large equation of the time difference, where you included, besides the ephemeris error, ionosphere and troposphere, there's the bias of the receiver, there's the bias of the satellite, there's the multipass error, and there's the random error. There's also other errors, for example, errors of relativistic effect. You might have heard of Einstein and the theory of relativity. So, but those can be, encapsulated there. So this is the equation. The idea is that you linearize this equation, transforms into a set of linear equations that you can then solve. Probably you even learned that here, how to solve linear equations, right? So you have 4 unknowns, and that's why you need 4 satellites. The 4 unknowns are x, y, z position, which you would imagine, but there's also the bias. You can actually solve for the bias of your clock. That's why you don't need a good clock. It can be an unknown because it's always the same bias for all satellites. It doesn't change. So, and you have 1 equation per satellite. So you need at least 4 satellites. Okay, and then finally, to finish up, there's also inertial navigation systems. So there's 2 of them. There's the Gimbal DNS, which uses a gimbal or stable platform. What it does is the vehicle moves, but the platform doesn't. So by just reading the angles of the gimbals, the platform stays isolated of the vehicle. By just reading the angles of the gimbals, you get an idea of what is the orientation of the vehicle. And there's also 3 accelerometers mounted perpendicular to each other, as well as 3 gyros. So you read the gyros, read the angles of the gimbals, you get the angles, and you read the accelerometers and you get the acceleration. Integrate 2 times, you get the position. That's the old technology. Newer technology is, instead of doing all of those mechanical appendages, you just basically strap down something like this to your vehicle, and you do all of those integration inside a computer. So you do all of those transformations that you see here mechanically, what the angles are, you compute them inside a computer using mathematics. So that's called a strap-down inertial navigation system. It has accelerometers and gyros, so 3 accelerometers and 3 orthogonal directions and 3 gyros. A model of the accelerometer is Newton's law. Sum of the forces is mass times acceleration. So you have the force that you're putting in the proof mass. So you have a proof mass. Let's say it's inside a car. The car accelerates, so the mass will accelerate. And for you to keep the mass at the same spot, you need to put a force. If you measure your force that you're putting and you divide by the mass, that's what an accelerometer is a specific force meter. But we always have gravity, always present in our daily life. So you're also measuring, there's another force applied to the mass, which is mg. So if you solve this and divide by the mass, you actually don't just measure A, you measure A minus g. So when you get 0 reading from an accelerometer, it means actually the acceleration is g. If accelerometer is in free fall, the reading is going to be 0. Okay? Because the accelerometer reads A minus g, doesn't read A. Okay? So that's something to keep in mind. So if you have any inclined plane, you have to keep that in mind. And a gyroscope, you probably saw what it is. Old technology is basically just a wheel that spins very fast. If you try to spin the wheel of your bike very fast, and then you try to change the direction of, it's spinning around an axis, and you try to change the direction of the axis of rotation, you're going to see how hard it is. Okay? So gyros tend to be spinning always in the same direction, and the direction stays steady. That's why they're good indications of an angle to a direction. The rate gyro measures the rate of the angle and measures the true rate plus bias. There's always actually a drift. So when you integrate this, that comes the problem that I talked about before, is that it will increase with time. So when you integrate epsilon in time, it's epsilon t. As time increases, the error increases. So these things have to be basically reset every now and then. And then there's Coriolis Theorem. I don't know if you studied already here or not, but it relates the derivative of a vector in one frame to the derivative of the same vector in another frame. So let's say, for example, a vector is an arrow. Let's say this is a vector. So you're seeing the vector in a given way in your frame, and I'm rotating, right? And I'm seeing the vector differently. So the change in the vector that I measure in my frame is different than the one that you measure in your frame of reference. And they're related by the Coriolis theorem. So if there's no rotation, they're the same. If I'm not rotating, I'm just translating relative to you, you see the same vector, okay? Because it only changes the magnitude, I don't change the right? So if it changes in magnitude, what I see is the same as you see, right? And then there's only two ways you can change a vector, either in magnitude or rotate or direction, right? So whatever I see in magnitude, you see as well. But if I'm rotating relative to you, then it's going to be different because you see the rotation, I don't, right? And with that, you can derive the equations of the INS. They are quite complicated, but this is the so-called velocity equation. This is the attitude equation. So you measure, by measuring the acceleration, you can integrate and have a velocity, and you measure the attitude, and you get a solution. So to finish up, I would like to talk a little bit about the navigation systems at Concordia. So you have now a good idea of what a navigation system is, what is out there. So what do we have at Concordia? At Concordia, you have a flight simulator, as I said. It's the only university in Canada, in Quebec that has a flight simulator, which you see here. This is the flight simulator with the visuals there. It's a simulator of the Beechcraft King Air B200, which is a turboprop twin-engine aircraft, as you see there. We also do, so we test our avionics there. We also do avionics for UAVs, uninhabited air vehicles. You see here a micro air vehicle that won the competition of best design of the Canadian Society of Mechanical Engineers in 2006. And this is the second version of that in carbon fiber. There's also flight control. We work a lot in flight control. And the way this is also taken from Wikipedia is kind of a neat picture. The way it works is the follows. There's primary controls and secondary controls. The primary controls in an aircraft, what do you have? Well, you can add thrust with the throttle controls. And you can also pull the stick or push the stick, which will change the pitch. So if you pull, you go up, pitch up. If you pull, you go up. If you push, you go down. And then you can turn that stick left and right, which will make the aircraft roll. And there's two pedals, and if you touch the pedals with your feet, basically if you put the foot on the right pedal, the rudder is going to turn right. If you put the foot on the left pedal, the rudder is going to turn left, and the aircraft is going to turn right or left. Okay? So those are the primary controls. Then there's the secondary controls, which are the trims, so-called the trims. If you don't want to be always fighting the aircraft, and let's say you actually have to be climbing a lot, okay, in order to not be having to put a lot of force in it, there's a wheel in an aircraft, or there's sometimes a trim button, that what you can do is you can pull the whole stick or the whole yoke further back to a given point and trim it there. So that then you just do small motions around that. Okay? So those are called secondary controls. You also have flaps for landing, which is a secondary control. Slats, which are the ones that come out towards you. Flaps go down, slats come out toward, and air brakes. The air brakes are the ones that go up when you land to increase drag and spoil the flow. So autopilots, this is now a work of my student Kyung Jae Baik. So what he did is he used the Wii, you probably recognize this. This is the joystick of a Wii, and he designed in MATLAB an autopilot with a free source, which is flight gear, flight simulation. And so that's one of the applications we have on autopilots. Another thing we did, as I said, We developed a Google Earth flight simulator at Concordia University, and we have it for teaching. We use it for teaching in our classes. It's very interesting. It connects MATLAB Simulink. Have you heard about MATLAB Simulink? Yeah. So it's basically, MATLAB comes from mathematics laboratory, so it's basically a program that allows you to do calculations. It has Simulink to model dynamic systems, and basically if you put a model of an aircraft in that dynamical system, and at each point, each step that you integrate the equations, you send all of the positions and orientation to Google Earth. Then Google Earth is going to show you the picture from a camera that would be at that position with that orientation. Keep doing this in real time, you have a flight simulator, right? So that's what we're doing. So you see here a picture, I'm going to show you actually the video. And we actually have used both together. So we have designed an autopilot, which is this feedback loop, is the autopilot. And that connects also to, adds to the command of the pilot, to a model of an aircraft, and then send to the Google Earth visualizer. So what I'll do now is just show you the video. So that's the result you get from the Google Earth simulator. So basically what you're seeing is, you see up there that we have also a map to see where you are. I would imagine it's somewhere close to the Great Lakes. So on the left, on the top left, you see the map, right there. Here you see what is called the gyro, the turn and bank indicator. So it gives you the sense of the accelerations for turning to do a coordinated turn. Here you see the compass, okay? And this is the image you get from Google Earth. So this is something that you can do in any PC if you have MATLAB with a license, of course, and the connection to internet. That's all you need with Google Earth, with the Google Earth plugin. Okay, Google Earth plugin is free. You have a computer, so the only thing that it's software to be bought, but I would imagine that probably here at Marianopolis exists in the labs here, is MATLAB, right? So MATLAB Simulink. And this is what you see from the simulator. It's quite spectacular. It's a pretty good tool to debug your Simulink diagram. So let's say you have a model of a complicated aircraft, and you want to simulate it. Instead of just looking at the plots of X, Y, Z, roll, pitch, yaw, right? 6 plots, you basically see what is happening in a realistic flight simulation. And of course, if there's a problem in the model and you go in a loop, then it becomes apparent when you just do the simulation. The way this was done and filmed was we were actually controlling the aircraft with a joystick. You need a joystick as well, by the way. But we can also do it to test our autopilots. So you can basically fly it on autopilot in Simulink. I would like to take this opportunity to invite all of you, whoever is interested, to come to Concordia and see it. We'll organize, if you're interested, let Dominic know. We'll organize a visit, and you can see this flight simulator and also the other Mechtronics flight simulator. And that's all I had, so I'll open up for questions. Thank you. Yes?
How does the guidance system of an aircraft smoothly transfer from data received from one source, for instance, let's say they're navigating with GPS, to shooting an ILS approach based on DOR technology? How does it transfer the guidance of the aircraft to sort of sharply turning it when moving from one source to another?
So one source of sensor, navigation sensor?
Right. If you're going from GPS navigation to ILS navigation, for example.
Right, but the thing is that you actually, that's a very good question. You don't need to shift from one sensor to another. What you can do is you can integrate all the sensors and do what is called sensor fusion. Means to do that is what is called a Kalman filter. I don't know if you heard about it. So it's a filter that basically gets information from all of the sensors and also runs at the same time a model of the dynamics inside. And so it gives you a nice mathematical way to have a nice blend and basically if you trust more the sensors or if you trust more the model, or basically it's a trade-off. It does an optimal trade-off based in mathematics. So that's how it's done. Is usually you pass through all of this through a Kalman filter, and then you fuse all of the information. And the Kalman filter as a filter is a smoother as well, right? So smooths things out. Any other questions? Yes.
You've got a lot of sensors and you're using them all together to get a more accurate idea, but how much redundancy is there? Like, can you lose a couple sensors without a large effect, or is it that if you lose 2 sensors, you're way off on your error?
Right. That's a very good question as well. Of course, in aircraft, we need redundancy because things can go wrong. In fact, there was an accident not that long ago, I believe in 2009, if I'm not mistaken, with an Air France from Rio de Janeiro to Paris, right? There was a sensor that basically with ice was the speed indicator with ice that has just frozen and stopped working. So usually aircraft have redundancy. So there's the sensor fusion part, and there's also the redundancy. Exactly to avoid the problem that you said, that if you lose a sensor, then you would have a second. But still, of course, even with redundancy, as in this case, problems do happen, right? So now it really depends on, the sensors that are more important, that you would have more redundancy. Depends also on the aircraft. If it's a general aviation aircraft, if you're flying a Cessna versus a Boeing, it's going to be different, right? So that is aircraft dependent. But the redundancy is always there because these are safety critical systems. Yes?
I actually had a question on redundancy as well. Something I've been curious about a long time. Does like a modern digital fly-by-wire aircraft, like an Airbus 380, does it, as one of its redundancies, does it have like traditional mechanical linkage to the control?
No, the mechanical, that's a good question too. The mechanical, for a long time, they kept both, of course. When they transitioned from the old mechanical technology to the fly-by-wire, of course, people are always, lives can be lost on this, so you have to be careful. So they kept both to have the redundancy. When they felt comfortable that they weren't using the redundant part, then they got rid of the mechanical linkages. Right now, there's only electrical redundancy. But one thing that it's now new and is going to be also, I think we're the cornerstone actually of another big development, which is called fly-by-wireless. As you know, wireless exists and permeates all spaces nowadays. You go to a coffee shop, there's wireless, right? There's wireless everywhere. You all have cell phones. You know how it works. Why not use this technology in an aircraft? In fact, there's lots of wires in an aircraft. You'd be surprised if you look at the wing, a section of a wing, how many wires are there. It's prone to problems, of course, wear and tear. Also, there could be short circuits. There could be several problems. Plus, it increases weight dramatically of the aircraft, and more weight, more fuel consumption, right? So the idea is, well, we can do a lot of things wireless. Why not do a lot? I'm not so sure, and a little bit of a disbeliever that we eventually are going to be flying wireless, fly-by-wireless, but fly-by-less wire is definitely something that people want to do, right? Which is different, right? So you keep some wired connections that are essential, but it might be the case as in the mechanical linkage that, you keep them and then one day you say, well, we actually don't need them, right? But, knowing as I know sometimes how the internet gets congested easily and things like that, so fly-by-wireless, I'm not sure we're going to get, but we'll see. But certainly by less wire is a desire. Another thing is that in aircraft, when you're building a new aircraft, several months before you deliver the aircraft, you can't even add a sensor anymore. This is a problem. This is costly. And the reason is because the wings and the fuselage have been designed to have a given section for a given number of wires. Anything you want to put extra sensors, you need to run a wire through the entire aircraft, which is very inconvenient. And so we went through this in music. Still remember the microphones that had a wire and now all is wireless, right? So we went through it now with the internet, with the cell phones. Why not in aviation? So there's lots of research being done there. Yes?
The GPS systems, how does the differential GPS system work to get these accuracies of centimeters compared to usual?
Right. Well, the GPS, what it does is it subtracts. So you have a base station. You usually have a ground station, let's say at an airport, or let's say, for example, you just actually have a rover here, and you have a ground station, for example, there with the GPS, and you have a GPS in the rover, okay? And so what it does is the ground station transmits the signals that it receives via radio, and so the rover will have access to the signals received by the station and the signals it receives also in his receiver, and it does the differencing of these two. And when you difference, there's lots of errors that are the same. They cancel. Okay? So there's differencing and there's also double differencing. Sometimes you take this 2 times the difference. And these are the 2 techniques, but it's by differencing the 2 that you eliminate certain errors and increase accuracy. Any other questions? Well, thank you very much for having me here. It was a pleasure. Thank you.